fluctuation dissipation theorem. Okay. So, is very important theorem, and I will not derive it in this class. I will state the result and I will motivate it. I will just use Langevin equation to connect. So, this relation connects fluctuation and dissipation. Okay. So, that is what is supposed to be, or Green's function and the correlation function. Okay. So, I will try to see show you what is dissipation, what is fluctuation in that relation. So, the statement is that x t is observable of a equilibrium statmic system. System is in equilibrium and this Hamiltonian is h naught. Okay. So, that is a Hamiltonian of the system which is function of x. So, this is in equilibrium, but I want to perturb it, I want to make it slightly non equilibrium. So, perturb it, bring in some fluctuation. So, my new Hamiltonian is h naught minus f t x. F is a force, a kick, basically you just apply a kick. Okay. So, this will create disturbance. Now, you can see that there is a, for h naught I can have Green's function, I have Green's function, no. So, for my system I define, I given h naught I have Green's function, right. I mean, in fact, Green's function is 1 by E minus h naught. Okay. So, there are different kinds of Green's function, but one of the Green's function is written like this. So, the Green's function, and so this response, system has a response. So, this has damping in it. Okay. So, there is the Green's function has some damping involved in it, but its response is x. X is the response, no, x is my wave response. So, x t prime, that is a correlation function, or its Fourier transform will be C of omega. Correlation, its Fourier transform will be C of omega. So, there is no wave number here, is a part, is a motion. So, I am thinking x is function of time, its Fourier transform will be in omega. So, the statement is that C of omega, this is a correlation function of x. So, this is x omega, x star omega. So, the C omega is connected with the Green's function. Okay. So, this is a fluctuation and there is a dissipation in Green's function, and the proportionality constant is this 2 kBT by omega. Okay, T is the temperature and omega is the frequency. Okay. So, you see the Green's function and correlation functions are not same, and the frequency omega has come in. So, this is, but this is not far away from equilibrium, in fact, it is close to equilibrium. My system was in equilibrium and I just give a small kick. So, this is supposed to be near equilibrium, this formula is valid only near equilibrium. Far from equilibrium, this formula will not work. And this proof, you can look at Wikipedia, we will get some idea about the proof, but it is quite complicated. Okay. So, I did not want to do it here. So, we will do a demonstration. Okay. So, I will try to demonstrate it, that okay, for a system this relation I satisfy the relation for given Langevin equation. Okay. So, I will basically do a demo. So, we start with the same equation, Langevin. Okay. Now, the zeta is of course random noise, but let us compute the Green's function first. So, to compute Green's function, what do? I put a source, right hand side delta t minus t prime. So, I put a g, this right hand side will be delta t minus t prime, and the left hand side will be gamma G t minus t prime. That is the definition of Green's function, and these are all linear systems. So, linear systems is what people normally work with. It is easy to derive a lot of relations. So, this is exactly solvable. We can solve in Fourier space, means omega space. So, by the way, we are using that Fourier transformer. So, f of omega, f of t is f of omega minus I omega t d omega. Okay. So, there is a minus sign here, and f of omega is f t e to the power I omega t dt, and this goes from 0 to infinity. T is starting from 0 to infinity, but sometimes people write minus infinity to the infinity, but we say, well, start from t equal to 0. If you put minus infinity, that means minus infinity to 0 is 0, but depends on the authors. Some people write here minus infinity to infinity as well, but time negative, okay, you can avoid it. So, here when I write this, so I assume that t is greater than t prime. Okay. So, response means if I do something, I get a response which should be later. So, if I do the Fourier transform of this, I will get minus this one minus I omega plus gamma. Okay. So, this d by dt will give you minus I omega, no. So, if I just what I am doing it here is this one, I am doing d by dt of this, right. So, minus I omega will come gamma, and g is replaced by g omega, g t minus t prime is replaced by g omega, and delta function becomes 1. So, straightforward, g omega is this 1 divided by minus omega plus gamma. Is very easy, no, is a linear system, straightforward. But Green's function is, look, playing a role everywhere, right. I mean, it is important, is the most important thing in field theory. Now, let us get to the correlation function. So, I do the Fourier transform of this. So, same thing, this part is that u t becomes u omega and zeta t becomes zeta omega. So, u omega, well, I made it a scalar right now, but you can prove a dot product as well if you like. Okay. So, zeta is supposed to be a vector, no? But let us assume right now 1D, let us just do 1D. So, u omega, so I take it below. So, u omega and u star omega prime will be this guy. When I do the complex conjugate, this minus I becomes plus here, and zeta omega and zeta star omega prime. Now, we do ensemble average, and the assumption that this zeta function zeta is stationary, that means its distribution does not change with time, and is homogeneous, that means zeta t prime is only function of t minus t prime. You understand, the correlation is, so if I shift the system by some time, I get the same correlation. Okay, so you shift t by alpha, t prime by alpha, this is unchanged. Okay, so this is called homogeneous system, and also stationary means things will not change, these correlations do not change with time. So, for that system, this derivation I will not do, this is zeta omega, c of omega, c zeta omega. So, this is the correlation of zeta, delta omega minus omega prime. Okay. So, this we did it for, I am not sure whether I did in this course, but look, for homogeneous systems, look, sin omega t, sin omega prime t, if I do average, this 0 unless omega equal to omega prime, no. because sin omega and sin omega prime, if they are not same frequency, they will cancel. If you take t large, integrate this. So, the frequency must be the same for it to be non-zero, and if it is same, then it becomes mod zeta squared. So, this is what it means. This is mod zeta squared and this is delta function. Okay. So, the left hand side, the correlation function, this also will be similar, is called C omega delta omega minus omega prime. So, delta delta you cancel it. So, C omega is this. Okay. Now, this part is left without proof, that this, since it is in a heat bath, so the zeta is representing temperature, fluctuation, noise, kicking. So, this is equal to 2 kVt, is proportional to temperature. Okay, is from algebra it comes at 2 kVt. So, my correlation function for Langevin equation is 1 over omega squared plus gamma squared multiplied by 2 kVt. Now, we have two functions, both C and G. We have this correlation function and Green's function. Now, can we relate them? Okay, look at the imaginary part of G omega. So, I multiply by complex conjugate. So, I omega plus gamma, omega squared plus gamma squared. I multiply I omega plus gamma both below and above. So, that take the imaginary part of this, what will I get? Omega divided by omega squared plus gamma squared. So, denominator is same as this one, right. So, I divide 1 by omega, I get this. So, replace for this, I am going to replace that. Okay. So, I get 2 kBt imaginary part of G of omega. So, there is a omega coming here, one omega is sitting below. Okay. So, that is a relation connecting correlation function with the Green's function. So, it is a demo, it is not a proof. Okay. Proof is more complicated, but this does tell you that the correlation functions are different and the frequency has come in now, and yeah, you have to be kind of do more work compared to equilibrium.